Hi, everyone. Good morning, and welcome to the first session of this workshop. It's a pleasure to have with us Gaurav Mahajan, who is a postdoctoral associate at Yale University's Department of Computer Science, where he is mentored by Dan Spielman. He is broadly interested in theoretical computer science and machine learning theory. Previously, he completed his PhD in the theory group at UCSD, advised by Sanjay Dasgupta and Shajar Loet. He has also spent some fun summers at Microsoft Research, Institute for Advanced Study, and Simons Institute. Over the next 4 days, he will teach us reinforcement learning in 5 hours. Over to you, Gaurav.
Okay. Hello, everyone. Yeah, I'd love to see some faces. So I don't know, if you guys want to turn on your video on the Zoom, that's fine. And hello to everyone. So let me actually, just feel free to ask questions throughout the bootcamp. And ask questions. You can just say hey Gaurav, unmute yourself. You can say, hey Gaurav, I have this question. This doesn't make sense. You can ask any kind of questions you want. And I guess a lot of reinforcement learning is a lot of definitions. So a lot of things I'm not going to go deep into formal stuff. So there could be confusions, right? So I'm going to keep it pretty informal, less than a paper, but I think a little bit at the level of a lecture note. So, we're going to do things very formally, but also not too formally. Okay. So, I guess, there are not too many people. So, in the beginning, I'll every one of you to introduce yourself. So, I guess the people on the Zoom, they can go, so let's say, Rohan, do you want to introduce yourself?
Hi Gaurav, I'm Rohan. I'm currently pursuing my JRF at ISI, Indian Statistical Institute in Kolkata.
Cool.
So yeah,
Nice, nice. Are you attending from Kolkata?
sorry.
Are you zoomed in from Kolkata or?
Yeah.
Okay, nice, nice.
Yeah.
Okay, so Vishnu Pratap, do you want to go in next? What are you up to? Are you a PhD student, undergrad? Okay, maybe we can go to the next one. Trisha, ready? Hello, are you undergrad? Or is that just an admin? Oh, that's probably an admin. Tanush Seal, hello.
Hi, I'm Tanush. Can you hear me?
Yeah, I can hear you.
Yeah. So I have just finished my undergrad from Institute of Mathematics and Application, and I will be starting as an integrated PhD student.
Oh, nice, nice, welcome.
Thank
Uh,
you.
yeah. Okay, can we have Shinjini? You know?
Yeah, hi Gaurav. I am an incoming PhD student at Leiden University. I just completed my master's from ISER Pune.
Okay, cool, nice, welcome. Let's see, Chandani Kumari.
Hello Gaurav, I'm an undergraduate student from the Delhi University.
Okay, cool, nice, welcome. Let's do Pratika Mishra.
Good morning, sir. This is Pratik Mishra, actually.
All right, Pratik. Hey, Pratik.
So I'm a MTech student at IIT Madras and CMC Vellore and Sri Chitra Tirunal. It's a tri-institute program. So
Okay, nice.
and I'm doing a joint degree right now in clinical engineering, which is a specialization of biomedical engineering. But I want to switch to applied maths after my MTech.
Cool. That's a nice switch.
Yeah.
Nice. Cool.
So
Well,
nice.
welcome.
Yeah.
Yeah, hopefully this will be useful. Yeah, we'll talk about some math stuff. So they're like some cool math problems that are kind of we can reduce some of the RL problems too. So there'll be some nice math in there. So you would probably enjoy that.
Nice to meet you, sir.
Yeah. Let's do Terry Kevin?
Hi, sir. Myself, Daddy. So I completed my master's from NIT Srinagar, and currently I'm doing a research project on gamma ray bursts at ICTS Trivandrum. I'm
Okay.
planning for my PhD in astrophysics mostly. Yeah.
Oh, cool. Nice.
Yeah.
I also started working on some like quantum information theory stuff recently.
Oh.
So I've been looking at physics with a, you know, a new lens. Like, wow, this is hard. So, so nice.
Yeah. Yeah. Nice to meet you, sir.
Yeah, same here.
Hi, Gaurav. Can you hear me?
Yeah.
May I suggest doing the intros in the break? I think we have a long break after this. We can like
Okay, cool.
easily
Yeah,
comfortably.
that's probably a good idea.
Yeah, okay.
Because I realize the people are kind of increasing, so maybe it's gonna take forever.
Yeah. You're talking popular, lots of people. Okay.
Yeah, and I'll love to talk to everyone, but it looks like there are a lot of PhD students, so you know we can just continue. But I have a question for you all. Can you see the iPad screen? You guys can't see that, right? Hopefully it's on the main screen.
Yeah, it is visible.
Okay, cool. Awesome. All right. Okay, so like I said, you know, feel free to ask questions, and this is gonna be a much, you know, better boot camp for everyone if you know everybody asks questions. You know, if you ask a question, it's gonna help other people because the question you have, you know, 10 other people will probably also have that question. So, you know, feel free to ask questions. And I guess for the people who are in the audience in the main hall, you might have to get up to the, you know, or get for the mic or something like that. So, you know, don't feel like worried about it. Just, you know, we can go slowly. So ask questions. Okay, so let me just, you know, dig right in. So what is this bootcamp about? Okay, so, you know, it's a RL bootcamp, but RL is like huge. So what is like the main thing that I want to talk about? And that's, you know, the main, like broadly what I want to talk about is reinforcement learning with function approximation. Okay. So, you know, I'm going to define what reinforcement learning means. So sorry for people who are new to the area, but on a very like, you know, high level, RL is used in, you know, training ChatGPT, you know, for designing game AI like Dota 2. I don't know how many Dota 2 players are here, but like, you know, Dota 2 AI is like really, really good. And for playing Go and so on, right? So all these applications, RL is used with some kind of function approximation like neural network, all right? And what that means is like all the algorithmic insights that we have with RL kind of have to now mesh together with all the stuff we know from supervised learning. Okay, so there's a huge motivation now because in practice, people use RL algorithms with function approximation, right? So the main reason, you know, we are doing this bootcamp is because, you know, it has a huge practical use. So in practice, basically all our algorithms use some kind of function approximation. Okay, and this is mostly for generalization, and we're going to talk about that too. You know, we will talk about, you know, why this is in some sense actually necessary. Okay, and I think this was kind of like the big insight that people have kind of built over the last 20 years. You know, function approximation has a huge, like it seems like, okay, you know, we just started using RL with function approximation, but even like 60 years ago, people were using RL with function approximation and they were getting really impressive results. Okay, so for example, you know, so if you go down, let's say 1960s, so at this point, Bellman Kalaba and Kotkin. Okay, they showed that there is actually, like, they did a huge experiment. They showed that function approximation, even linear function approximation. Okay, so it's too hot. I'm just going to write FA for function approximation. All right. So you can use, linear function approximation for really good, like, empirical benefits. Okay, so already in 63, people were moving on from like tabular state spaces to like these linear function approximation for generalization. And, more importantly, Samuel basically designed a checker playing AI using linear function approximation. Checkers, there's a game, checkers, people who don't know. Using linear function approximation. Okay, we're going to talk about what linear function approximation means. These words, they're not probably going to make any sense right now, but maybe to experts, this probably is making sense. Okay, so a big part of what I'm going to talk about will be about linear function approximation, and there's a lot of good. Somehow there's a lot of depth in just understanding linear function approximation. People who know supervised learning, linear functions like super like basic in some sense, but somehow in RL there's a lot of like computational differences, which was surprising, I think, to me at least. Learning somehow linear functions in supervised learning is computationally easy. You can just, but you can do Gaussian elimination. But for RL, we can show that it's as hard as SAT. So there is like some like big differences in just learning, RL with linear function approximation. So this is, something we're going to talk about a lot on day 3 and day 4. So this is really good CS3 work that we can do here. Okay, the second thing is that just from like a theory perspective, it's just a nice problem to work on. There's a lot of cool things. So nice theoretical depth. So cool math. Okay, so, with that, I described the goal for this bootcamp, so the goal is to basically, talk about recent advances and techniques to analyze RL with linear function approximation or just some kind of function approximation. Okay, so how do we achieve that? So how do we formalize reinforcement learning with function approximation, and how do we analyze sample complexity or talk about algorithms in this setting? Okay, so what we're going to do is we're going to do basically 4 days. Okay, so on day 1, I'm going to basically just talk about RL basics. Okay, so this is going to be probably boring for experts, but I just want to start with setting up the whole definition from super basic. So if you're not even from RL field or haven't seen RL before, this will be totally fine, but you would need some kind of mathematical maturity and hopefully not too much. So if you have done some linear algebra course, then you should be totally fine. Okay, so we're going to define what an MDP is. Okay, so that it's going to be day one. And then, what a policy is, what are value functions. Okay, so day one is all just going to be definitions. And to be honest, like this is the, the worst part about RL. That's the thing I hate about RL, definitions. But, once you are done with the definitions, then it's all pretty cool. So this is going to be, unfortunately, a little bit dry. But some people like definitions. So, this could be fun for those people. And then we're going to move on to day two. That's where the fun begins. So I'm going to talk about, these really cool algorithms, gradient-based algorithms called policy gradient algorithms. Okay, so let me just say, this is fun. Okay, so these are simple gradient-based algorithms, but variants of these algorithms are really the workhorses, which make ChatGPT train, so they have huge impact. And they're, just so simple, but like they work great. So, these are the workhorses behind, ChatGPT training. Really cool algorithms too. Okay, so because they're so simple and they're so useful, we're going to spend the whole second day just talking about them. And we'll end with, actually coding it, coding these algorithms from zero, so you just need PyTorch and we'll code it up and we'll, use these algorithms to solve cartpool. Okay, so what is cartpool? I guess, people from physics, if they're here, they might already know, but like this is like a super, canonical control problem. Okay, and if you want to solve it using math and physics, right, it gets complicated, all right? You need to know like a lot of physics and, it's hard. But you train these algorithms that, which are super simple mathematically, and these algorithms are going to solve these cartpool problems, exactly. They're, approximately, but like they're really good at it. So, that's amazing. You have a simple algorithm. I can describe it to you, in one day. We'll code it up and just solve a cool math physics problem without knowing any math and physics. So that's impressive. Okay, so this is like, my favorite part. So, but it requires some work. So what do I need from you guys for second day? So if you're attending day two, then there are some setup instructions. It's going to take, maybe 5 minutes on your PC to set your PC up. So I have instructions. They should be in the schedule that you guys have. But if you also go to my last name, Mahajan dot github.io. If you go to my website, there will be a link for ICTS RL Bootcamp. If you go there, you'll have access to notes and you will see instructions on day two. All right, so it's going to take 5 minutes and it will set your system up for coding. So it will install Xcode and install the environment so you don't mess up your PC. Just do it in virtual environment and install PyTorch and the games. All right, so and that should take like 5 minutes if you're on a decent internet. The commands only 2-3 commands, so it's super easy. But if you do those instructions before day two, then I can basically just go in and teach you all about the code, and we'll code the cartpool together, and everybody would have a pretty good, decent solution of cartpool invariance. All right, so yeah, this will be fun. So yeah, just if you're attending day 2, then please do the set of instructions. And if you don't find it, you can always email me, and I'll give you a link to this instructions. Okay, so let's go to day 3. Okay, so day 3, we're going to talk about, this is going to be more theory now. So day 3 and day 4 are mostly theoretical. But here we're going to start talking about what does it mean to be an efficient RL algorithm? What's a good RL algorithm? All right. So there are 2 notions of good RL algorithms that I'm going to talk about. And the first one is going to be a data efficient. Oh my God. Data efficient RL algorithm. Okay, so what's a data efficient algorithm? So we're going to say, an data efficient algorithm does little amount of interaction with the environment. So we're going to measure it in how many interactions this algorithm does with the environment. So with a simulator or an environment to find a good policy. Okay, so that defines what's data efficient algorithm. We're going to figure out like when can you design a data efficient algorithm? What are the conditions? It's going to be like most of the times, it's going to be pretty hard to design a data efficient algorithm. We're going to see like, oh, if you have these kind of assumptions, then makes it easier for your algorithm to learn what the best policy is. Okay, and day 4, and this is again like one of the areas that I like the most in RL, is going to be talking about computation. So what does it mean to be a compute efficient RL algorithm? Okay, so we're going to define this as some algorithm which uses not too much GPU. GPU is money. To get a GPU hour on some server, you need to pay money. So this is important, right? So it's basically ask how many GPU hours, or let's just say, more leniently, it's like compute, how much compute you need. But this is basically just GPU hours. How much compute do you need to find a good policy? Okay, and this is gonna be pretty nice. It's gonna be a nice question, and it's gonna be fun. Okay, and so last thing, ask questions. Okay, so I'm gonna pause here. Ask, how does this sound like? Do people want to do something else too? Like something that they felt like, oh, I would like to know that about RL. Is there any questions like that? If there are no questions, that's great too. I'm just gonna pause here to see my chat. Are there questions here? And is there any question in the audience? Okay, everything good? Okay, cool. All right. Okay, so we can start with day 1. So I'm going to talk about RL. What is RL? What are the definitions here, right? But before I do that, I'm going to start with like 2 very simple problems. And just say like 2 example problems. Okay, so what do I mean by these two example problems? I want to describe, scenarios. Or problems that I would like my RL algorithm to solve. Okay, so these are basically the motivating, I would say, like the spectrum of problems that people wanted to solve with RL, and that's why they created RL. Okay, so I mean, figuratively. So, these two problems are this slot machine problem. Okay, so that's the first problem. Okay, so in the slot machine problem, you have slot machines. Okay, I don't know how many people know what a slot machine is, but if you go into a casino, right, there is this machine in front of you, and there's an arm to the machine. Okay, and basically what you do, if you pull the arm of the slot machine, it gives you some reward. Okay, so it's just like some kind of casino game. Okay, so we have, and usually in a casino, there are like many of these slot machines. So let's copy them. Okay, so you have lots of slot machines. Okay, and let me be very concrete. Say you have 300 slot machines. You go to casino, you see so many of slot machines. Okay, and like I said before, if each machine, basically when you pull its arm, it gives you a random reward. Okay, between 0 and 100. Either it gives you $0, you don't lose anything except maybe the game, right? And if you win, you get something between 0 and 100. Okay, but because something happened, you can't play forever. You have to go out with your friends. So you can only play a total of say 1,000 games. You can only play this 1,000 times. Okay, so you can go to a slot machine, pull its arm, get some money, some random money, right? And then you go to another machine, you pull it arm, you get some money. You can pull the arm again on the same machine, right? And really your goal is earn money, right? So your goal is to maximize your expected return, okay, or reward. Okay, so you're gonna run, you're gonna do this pulling 1,000 times. You wanna earn as much as you can. You wanna get a lot of money. And inherently, in this kind of definition, there's like a belief, right, that some slot machines are probably just good. They're better than others. In some sense, you're kind of trying to identify, by pulling these levers, which ones are the good slot machines, where when you pull, you get like always 100, right? Maybe there are some machines like that. And there are some machines which always give you 0, so you never want to run that, all right? So there are two basically impulses. Okay, one impulse is to explore. Okay, you want to explore by playing different slot machines. You haven't seen 100 yet. So maybe there is some machine who's going to give you 100, right? So you're going to explore by playing slot machines you haven't played. So unplayed slot machines. Okay, but then there's another impulse to exploit, right? You pulled a handle on a machine, you got 100, and you probably don't want to explore anymore. Like, okay, maybe this one gave me 100 once. Maybe if I do it again, it will give me 100, like, so you want to exploit by playing slot machines, which are, have performed better than other people up till now, so by playing the best slot machine up till now. Okay, so there are these two impulses, and RL is going to balance these impulses. It's going to balance them optimally. So, it's pretty cool, right? That somebody can solve this. Okay, so that's the first problem. And we would like to solve it. And RL will help us formalize this problem first. Right? Right now, the way I've kind of written it, it's like a little bit vague. But RL is going to formalize this problem, and then it's going to solve this, all right, optimally. So that's pretty cool. Are there any questions about this problem? At this point, I should definitely pause. Feel free to ask questions. This is, bread and butter of RL. Okay. No questions. Great. Okay, so second problem is about playing chess. Okay, so in this problem, you are an AI, right? You're an AI agent trying to learn how to play chess. Okay, and the interaction model, the way you as an AI agent can play chess is that, at each turn, an AI is shown the chessboard or the configuration of the chessboard. And they're asked, what's the next turn? Or next play. Or, move. Okay, and so if you're an AI agent and you're trying to solve this problem, in principle, you can solve this problem by learning best move for each configuration. Okay, so in principle, if you learn what's the best thing to do in each configuration of the chessboard, right, then you know how to play the game optimally, right? That's, almost seems like recursively true. Okay, so if you learn what's the best move for each configuration, that means, right, it implies that you learn how to play optimally. Okay, that's pretty good. But the problem is, learning the best move in each configuration is hard, right? Okay, I mean, there's obviously problems that the number of configurations are too many, right? I mean, famously, there are more than the number of atoms in the universe, right? So it's a huge number, right? But even if you can play around with those state spaces and you don't have to like enumerate all of them, you still have to find out what's the best move in each configuration. And that in itself seems much harder, right? And the reasons for that is, first, you only receive feedback if your move is good or not at the end of the game. You either end of game. You either win the game, in which case, you get to see like, okay, whatever I did, I won the game, or you lose the game at the end. And then you have to figure out which action caused it. And that's the second problem. It's really hard to determine which action or sequence of actions led to the outcome, right? You play a game, you lose at the end. What was kind of the most important part of the game? Which actions or sequence of actions are responsible for the outcome? Okay, and that's really hard to do in chess. And this is true in a lot of settings, in our settings. And this problem is basically called credit assignment problem. Okay. All right. So so there are these two problems, and RL is going to solve both of them optimally. Okay. So now we're going to see, a model which solves both of these problems. Okay. Questions. So now I'm going to talk about our model, but are there any questions up till now? I'm sure a lot of people know what chess is. They play chess. So, okay, great. It's going great.
Our audience questions, please feel free to raise your hand, and then volunteer will pass the mic to you.
Thank you, Jatin. Oh, is there a question? Okay, there is a question. Okay.
Hello, sir. So when you said that learn how to play optimally in each chessboard configuration, doesn't the best move in that configuration also give us the entire, like what the best move will be in the next step as well, in 2 steps after that as well? Aren't all these informations also needed to find the best possible move for that particular configuration?
Exactly. Yes. And that's really like what I'm saying in this. Eventually your goal is to learn the best move in each configuration, but you're saying, yeah, those are all related. So somehow it becomes like really hard, like, what is the best move? Like right now, if you have to figure out that, you have to figure out what's the best move in the future. So,
So
it gets hard.
so my question was, isn't this same as saying what is the best move in the first step?
So it's going to turn out, if you can figure out what's the best move in the first step, and recursively you can figure out, what's the best move in the second step, then you solve the whole, policy. So you know the whole thing. But the thing is, like, when you're trying to design algorithms, you can't start from like, what's the best move right now? You basically have to start from like the bottom. Oh, what is the best move right before I end the game.
All right, I see.
That's
Thank
gonna
you.
be like the most easiest thing. But yes, you're right. If somebody gave me a function to figure out what's the best first move, then I can use that to solve the whole chess. You're right. And this is basically, I don't know if you have read this, but like Turing wrote a paper on playing chess. And his like argument for like, what should we use for playing chess is kind of derived from like, oh, what's the best first move? So it's a really good question.
Okay, thank you, sir.
Yeah, it's a good paper. Anybody who works in RL should read Turing's paper on RL, on playing chess.
Hello. Yeah.
Yeah.
So I have a question regarding the slot machines. So I'm a little confused. You said they are random, but you still have good machines and bad machines. How is that? If they were truly random, then they're all same, right?
Right. So good. So I guess I never defined the randomness. So yes, they're not truly random. Not all of them are random. So what happens is like, the model basically specifies that each machine has like some number hidden inside it. So for example, this machine has some number, say, between 0 and 100, like say 10. This has say 0, and this has like say, 100 or 90. And basically, what I'm saying by randomness is that when you pull the arm, you get some number between 10 plus, 0 and 5. So randomness is here. And then when you do 0, you get something between 0 plus something between 0 and 5, and 90 plus something between 0 and 5. So the good machines are these like things which have like, higher base number. This last machine is better than both of these machines. So the expected reward is what we kind of like trying to get at. Does that answer your question?
Yeah, I think it's clear now.
Okay, cool. Awesome.
Yeah, hi. So in the chess game, the best move is in response to the other players' moves, right? So are there any assumptions made about the behavior of the second player?
Very good question. I'm very surprised that you guys are asking these questions because when I first worked in this area, I actually did not pick up on that. But that's a really good question. And like I said, Turing talks about this problem too. So you guys should definitely read that. You guys are, I think, ready for his paper. But in response to your question, yes. So the way it depends is how we're gonna model it in the in the RL thing, but it's going to decide the complexity of your transition function in some sense. So your opponent can actually play a randomized strategy too, right? Like so like in obviously like chess is deterministic, but they could pick a deterministic action randomly, choose between policies. So yeah, it's pretty interesting. It's pretty interesting. So but you can model this, and it will be part of the what you call environment in RL. So when I actually go over the RL model, I'll actually use chess as an example. So this question will be much clearer then. But it's a very, very good question.
Thanks.
Am I audible?
Yes.
So I had a question about the chess problem and like a slightly broader question as well. So I think like if I understand correctly, the problem is that the game tree is like growing exponentially and backtracking from the outcomes is computationally quite difficult. And I think that is a common characteristic for a lot of these two-player combinatorial games. So whatever we will discuss like in the future, does that translate to other two-player combinatorial games as well? Since like I'm assuming that the problem we're trying to solve for is how computationally expensive it can be to actually find the like
Or
ending.
how many games you have. So there'll be two questions. One is like this data. How many games do you have to play? How many times do you have to interact with the chess game? And the second question will be like, once you play all these games, how long do you have to ponder to figure out what the best strategy is? Sorry. Yeah.
Yeah, so I guess like the broader question was that whatever we develop for these, like this particular game of chess, let's say, does that
Right.
translate to other games of similar nature where there's sequential moves being played and again, keeping track of it combinatorially is quite difficult.
Yeah. I mean, I think it will depend on if they can be fit in the RL model. But RL model is like so like general. Like I would say like to the level that it's like hard. So yeah, but I think a lot of games can be set up as MDPs. But I'm sure there are games which cannot be set up as MDP either. So it's good question. A lot of games can probably be solved in using RL.
Thank you.
So I've got a question on chess, right? I think we're assuming that it's only the state of the board at a particular point that matters. So why not the history? Why not the path that was taken? Something like a Markov. You're
Right.
getting right. The path would kind of indicate the intelligence you're playing against. So why is it not a function of that?
Yeah, I mean, I guess, well, actually, if you forget about all like algorithmic aspects of it, then in some sense, like, the state that you're in, you could store more information in it. Right? You're bored and then more information like what you're saying. So that's always possible. But I'm just kind of talking about like the easiest kind of setting. But you're right. We can make this harder. Maybe the state has, more than just the configuration, some more information about the player that you're playing against. Yeah, that could improve the optimal policy. Yeah.
So I'm talking about the history of the board, as it evolves over each move.
Yeah. So, you can set up you can set up that problem as a RL problem too. So you will see later on, this problem, like the problem I'm talking about can be set up as RL, and the problem you are talking about can also be set up as a RL problem, where you use the whole history instead of just the current state.
Just a quick question. We're talking about a 2D state space here.
Good question. I'm gonna define state space soon, and then this will be very clear. I'm actually gonna be like talking about state spaces in general a lot. So, they're gonna be a very important aspect of function approximation. So,
I mean, the reason I'm asking this question is, let's say if you take the example of a horse, and a horse only has a certain movement that is possible within the entire state space. So do we are we able to put in element-wise constraints while solving this? That is what I'm trying to ask.
Yeah, I think you can do all these kind of stuff. Yeah.
Okay. Yeah.
Okay, so I think I'm gonna move on because I think I'm short on time. But hold on to your question. I think a lot of these questions will probably be solved by the next stuff. All right. So now I'm gonna talk about RL model. Okay, so what is this model that we can build to solve both of these problems? Okay, so the two entities in this model. Okay, one is an agent. Okay, and the other is called environment. Okay, so I'm going to describe everything formally, but on like, on a high level, basically, agent is the AI playing the game, and the environment is like the chess game. Okay, so the agent basically starts in some state, and then based on that, it tries to pick the next move. We're going to call that an action. And in response to this action, the move that somebody played, the environment or the state of the chess is going to change. It's going to change from, some state to another new state. Okay. So it's going to give that state to the agent. And also it's going to give you some reward. Okay. So each step there is some reward. And this reward could be 0, but we're going to analyze that mathematically. So we allow the possibility of a reward. Okay, so this interaction, the thing I just said informally, we're going to formalize this now. Okay, so this interaction is formally described by a Markov decision process. Okay, so this is to, formalize this above, interaction. You have an agent and environment, how are they going to interact? And to describe this Markov decision process, I'm going to describe this by, a state space. Okay, I'm going to notate it with S. Okay, so this is basically the set of all possible states. Okay, for example, in the game of chess, this is going to be all possible configurations of the board. And like one of your friends said, you can design as many different kind of states. You can have a state which contains the history up till that state in some sense. So all possible sequences of states. Anyways, for now, we're going to keep it simple. For chess, game of chess, the state space is going to be all possible different configurations of the chessboard, as an example. Okay, so what else do you need? We need to define what action is. Okay, so we'll have an action space denoted with A. Okay, and this is the set of all possible actions. Okay. And then we need to define, what happens when an agent takes an action. And that's given by a transition function. Okay, I'm going to translate it by T. It's a function from set of states. You're in some state, take an action, and you go to some distribution over next states. So transition function, tells you like if you're in some state and you take some action, you're in some state S, you take action A, what's the distribution over next possible states? Okay, so in chess, if you are in some state and you pick some move and your opponent is also playing deterministically, this is a deterministic function. You end up in some fixed state. So there's not going to be any distribution over next state. But if, there's some randomness, your opponent is playing a random strategy or something like that, then, it's going to be a distribution over next states because you're going to play a move, the board is going to change in some way, but then the opponent is going to play a random move, and that's the state that you're going to end up with. So transition function takes in the whole open kind of point. Okay, so this tells you, if you're in some state, take action A, where do you end up? Okay, then you have a reward function, R, which takes in a state and an action and gives you a distribution of your next reward. And this is some number between 0 and 1. This is just for like, standard, between 0 and 1. But you can pick any number here and the theory remains the same. Okay, so this gives you your next reward. You also need like some way of like starting the game. So you need an initial state. In your state space. So, every game basically starts from some pre-decided initial state. Okay, and, some people usually like to say like, okay, what if like the initial state is like coming from some distribution, so it's a random starting state. And you can basically show that, you can assume the initial state is deterministic without loss of generality. You can assume is chosen, deterministically. So if the initial state is coming from some distribution or is something fixed, that doesn't change any of the setup. Okay, because you can always add one more step to your transition function. Okay, and the last thing we need is a horizon. It's just some natural number. And this basically specifies, number of times you play a game. Interact, the agent interacts with environment before restarting from the initial state. So you basically start from the initial state, take an action, take another action, take horizon many actions, and then you basically just start from the initial state again. All right, so it's just some kind of fixed number. You cannot play further than that. Okay, and so this is how, the MDP works. So see, and this is how the interaction looks like.
Hey, I have a question here. Sorry, since you're talking about chess, it might be, of course, that some kinds of, so you said without loss of generality, you could assume that the initial state was, but of course it could be that some kinds of initial states are not reachable from other initial states. I mean, if you look at Fisher random chess, some of those states are not, are not even part of the state space that you would get if you started with the standard configuration. So, I mean, could you explain this a little bit more? Initial state might also determine what are the configuration space in the future.
Oh, yeah, for sure. Yeah, definitely. Well, what I meant was like, when you describe a problem, you have to describe an initial state. So this is part of the problem. Like you pick a state and you put there. And so, for example, in chess, the initial state is like, all the, wow, I don't know much about chess. So all the things, they're basically arranged in a row, right? Like so that initial state is going to be like some fixed initial state.
Yeah. So you could have other initial states, and so that's also part of your problem. Yeah.
I'm saying like that could be like a different, that's a different variant of chess. But yeah, you could also play that. Yeah, but it's a good question. Yeah. All right. Okay, so how does the interaction look like? Okay, so the agent starts in some state S0. So I'm just kind of like setting up notation here. So the agent starts in state S0. And then for each time step, t from say 0, I should choose 1, all the way to h minus 1. Never mind, let's do 0. Yeah, this always is a headache. Okay, so, at this point, agent would observe the state. So, you say it's S0, and then agent observes what state you are in. So, at time t is st. And then the agent selects an action at from the action set using some policy, So that's also the definition of policy. So this thing basically comes from some policy that a policy is just some function from states to action. Okay, and then because of this choice of action, the environment provides a reward, RT, which is going to be something random between 0 and 1. And RT is basically sampled from the reward function for S, I. Okay, so you see that. And then environment transitions to the next state. ST plus 1, which is sampled from a transition function. So this should be ST, AT. Transition function on ST, AT. Okay, so the agent starts in some state S0. Then it basically does this loop where it looks at its state, chooses action AT, and because of that, the environment gives it some reward RT from this reward function and some random state from this transition function. Okay, so there are two sources of randomness, one coming from your reward system and one coming from your transition function. Okay, and the goal, so the person who's designing the policy, right? The goal is to solve this optimization problem. Which is, just to find the policy which maximizes the expected reward. So let me just write it down and then I can explain it. Okay, so you want to find a policy which maximizes your expected sum of reward. So you choose an action, you get a reward. Choose another action, you get another reward. You want to maximize the sum of these rewards. But this sum of rewards is random, right? You're getting some randomness from your transition function, getting some randomness from your reward, but you also get randomness from a choice of your actions. If you're playing some kind of random strategy, then you're getting some randomness from there. And you want to maximize, your expected sum of reward given your choice of policy. So you're going to maximize over the choice of policies. Okay, and in general, in any of these exact problems, you're usually also happy with approximately optimal. Okay. So approximately max. And also doing that with high probability. So you will have some strategy of finding this policy, and that policy is going to be very close to optimal with some probability over your algorithm. Okay, this is very standard supervised learning stuff. Okay, so that defines RL problem. So in RL problem, to describe RL problem, you need to describe an MDP, right? You need to define what a state space is, what's an action space, what is the transition function. If I'm in a state, I pick an action, how does my state evolve, right? What is my reward? For example, for chess, your reward is going to be 0 all the way until, you end up in a state where you win. In that case, you get reward 1. Okay, in Horizon, in chess, it could be a time limit. You cannot play a game for more than these many steps. If it happens, everybody loses. You get 0. All right. Okay, and then your goal is to find a policy. So for every state, you're going to figure out action. So policy is just figuring out what action to take in each state. Find this policy which maximizes the expected sum of reward. Okay, so that's our model. Do people have any questions? I'm assuming there's gonna be a lot of questions, but or maybe not. Maybe everybody got it. Okay, I see somebody asking a question.
Hi, so I wanted to ask, in chess, for example, the actions I can take in a particular state depend on the state I'm in, right? So if a piece gets eliminated, I can't move that piece. So is there any way we're constraining the action set based on the current state that I'm in?
Yeah, you can. Yeah, it's I didn't talk about it, but it's very easy to do that. Your complexity usually depends on like maximum number of actions or something like that, but yeah, you can do any kind of constraining. Okay, great question. Perfect. Let me look at the chat. Oh, there are a lot of questions in the chat. What is meant by the best slot machine? Oh, I think I already answered that question. Right. Okay. Cool. No more questions. I think I don't have much more time, right? Is Jatin here?
Hi, I think you can take an extra 5 minutes.
Okay, awesome. So I'm going to define value functions tomorrow and what an optimal policy is. But like, I want to just take the last 5 minutes talking about what's going to happen tomorrow. All right. So tomorrow we're going to talk about some simple algorithm to solve this problem. All right. So simple algorithm which satisfies this goal, finding the optimum policy approximately with high probability. Okay. And it's going to be a gradient-based algorithm. It's called policy gradient algorithm. And we're going to tomorrow code it up in PyTorch. So please remember to do setup. It's a chapter 2 in notes. So, okay, so let me write it down. Tomorrow, if you're attending tomorrow, do setup. Look at chapter 2 in notes. Okay, and the link of the website is go and then my last name .github.io. All right, and then if you just go there, you'll see there's a link to ICTS. Okay, and today I went over chapter 1. Wow. Okay, so you have questions, you can go to the notes. The notes are much better than how I say anyways. I wrote them, I spent some time on them. So, so the notes are much better than me. So read the notes, and if you have any confusions, you can email me. If you're already on my website, you'll see my email there. Just email me if you have any questions, don't feel bad. Do add somewhere in the subject that this is about RL Bootcamp. Okay, so you can start with like RL Bootcamp, maybe RL Boot. Yeah, just start with RL Boot in subject, and then just send me an email. All right. And yeah, so if you're attending tomorrow, remember to do the setup, because otherwise it will be hard for you to follow. Okay. All right.
And you can take another 5 minutes actually.
It's okay. I think we can just take a break. It's about questions, questions for sure. If people have questions and if they didn't get to introduce themselves in the beginning, feel free to introduce yourself. And I'm here, so we can talk.
Are there any questions? You can raise your hand.
or we can just talk, if there's no questions, I'm here. If you have any RL related questions, or talk personally, we can end the boot camp and we can just like talk.
Hello. So my
Oh,
question
hello.
is, you said that this is at least as hard as the linear function approximation is at least as hard as SAT, right? Is that
Oh,
finding the optimal policies as hard, or in what sense is it as hard as that?
oh, well, I guess I haven't talked about it. That's like day 4. I'm gonna talk a lot about that. That's like my favorite topic to talk about. Uh, so I'm gonna define, what does it mean to be hard, and I think you're talking about computational hardness, right? So I'm gonna talk about what is computational hardness, and we're gonna show that actually, yeah, like I'm going to define what linear function approximation means, but RL with linear function approximation, in the worst case, is as hard as solving SAT. And in the sense that, in the weakest sense, like not just finding the best policy, even finding something which is like better than random, can be very, very hard.
I see.
Yeah,
Okay.
and so computational stuff, you need to do some. So I have to define like under what. So yeah, so it's gonna be under ETH. So, but we'll go over that. Yeah, that's the fun part. We're not gonna rush into it. But good question. Any more questions?
Feel free to raise your hand. Or in the chat. On the Zoom chat also, anybody can ask.
I mean, I have a question for you all. What got you interested in RL? I got into RL watching all these like nice video lectures from like Andrew and other people yeah. And also just looking at Dota 2, the AI for Dota 2. Did you guys also like RL because of that?
You can put your answer in the chat or raise your hand if anybody has a interesting comment. I have a comment. I think I like RL because I think the point of life is RL itself. Like we're all doing reinforcement learning on our own.
Yeah, that's true. Live life optimally. Yeah, I agree. Sorry. I mean, if there are no questions, we can just end it sooner and, enjoy the rest of the day. It's going to be, I think, a lot of fun at ICTS. I'm missing out. I should have been in ICTS.
Sir, I would actually like to answer your question.
Yeah.
So I actually got interested in reinforcement learning because I'm interested in the function of the brain. So I think like compared to other AI models, reinforcement learning is very similar to how we humans or living beings actually get to learn. So that is why I got interested in reinforcement learning. It gives us a mathematical insight on how the brain functions.
Pretty cool. I mean, I don't know much about how brain functions, but that seems like pretty nice, endeavor. So best of luck.
Thanks.
I know, sorry, I only know the last name of this guy, like Papa Dimitro. So he's a big shot in CS theory. So he did a lot of like recent work on like designing calculus of brain. So I like his work. So, if you are interested in how brain works from a CS theory perspective, definitely check out those videos. They are fun. Or I mean, just email me and I can send you the video link. That's probably easier. Sorry, I didn't get your name. I cannot see who's talking, but
Sir, this is Pratik.
Okay. Hey, Pratik. Free feel to send me an email and I can send you the
Sure, sir.
Yeah.
So there's a question in the chat. Gaurav, could you please answer that?
Oh yeah, for chess, is it required to define some reward structure for intermediate steps? No, right. So, the reward is going to be zero. For chess, it's going to be zero everywhere except when you win, you know? So you don't have to give some reward. So this thing basically allows for zero reward too. But it's a good question, Yeah. But for example, like if say chess had some reward, in the intermediate steps, would that make the chess problem easier? And I think this is like really like how AlphaGo solved the problem. It said, I'm gonna do this, I'm gonna like design this huge value function, which is going to tell me how good my action is. So this is basically how they solved chess. So we're gonna talk about this tomorrow. It's a good question. And this is like amazing why any of these games can be solved. These value functions that I'm talking about, I'm gonna define them tomorrow, but like these should be like really hard objects, but very simple algorithms, grain-based local improvement algorithms, learn these value functions. So yeah, it's amazing. And it's just so much like if any of you know Dota 2, I don't even know like what the value function for Dota 2 should be, but these games, these AIs, they know how to play it. They are really, really good. Okay. If there are no other questions, we could just end for the day. Have fun in other places in ICTS. I feel like this is gonna be a great workshop. And I wish I was there, but you guys should have fun in my stead. All right. So have fun.
Great. Thanks, Gaurav. See you tomorrow morning.
Yeah. Yes, yeah, Jatin.
Okay, see you.
Well, I'll be here if people have any questions though. So I'll let other people leave before I leave.